Okay, I think we can start. So thanks everyone for being here. So this is the first talk of this experimental project, like Compassionate Math Seminar Series. I would like to give a little bit of backstory, how this all started. So like about a year ago, Ted, Paul, and myself, like we started meeting on compassionate math and like category theory, and then the group grew. Like I met Niels and like other people joined in. A lot of fun ideas and like interesting ideas has been floating on in this group. And this is our first experiment in the outside world. So we are like, we want to make a little bit of change in math communication and to bring more people into math. And so like this seminar series itself rose out of the desire that we want to talk math or about math that we don't get to really hear in regular math talks. So to be more artistic, creative, and accessible and approachable. So that's kind of the aim of this series. And I would say like the talks in this series is going to be like semi-formal or semi-informal, like so formal in the sense that we will have a few slides, but informal in the sense we are leaning in more on the conversational style. So it's more about engagement between the speaker and the audience, and it's audience driven. So and so we have a wish list, like what we want this series to be, but we don't know how to get there. So this is more like an experiment, and I welcome you all to participate in this and help us shape this shape the format of the series. So the first talk of the series is by Niels. I met Niels through Pavel like a year ago, and we have been in touch. So how Pavel introduced Niels to me is like he's a master of games. He's a master of Dungeons and Dragons. So Niels is a very creative game maker, and he's very passionate about category theory and mathematics. And so let's hear what Niels has to say today. Niels, the stage is yours. Thanks.
Oh, thank you very much. And thank you for this honor of launching this seminar series. I see a lot of different people from different walks of life in the audience as well. So thank you for the introduction. Yeah, so this is really a merger of different interests. Like I like video games and I like mathematics. And I really believe that video games can be a good tool for learning how things can behave and learn about mathematical structures by interacting with them without actually needing to know the definitions. It's like knowing how to use these structures over having to completely formalize, having the formalization be the job of the underlying AI or the underlying game or game master or organizer, and have you be the person that uses it and pokes it and looks at it. And so I have a bunch of slides. And so I do want to say that this work is, well, it's called Relational Molecules. And I hope you can see the slides. And this kind of structure, these relational molecules are not anything particularly new. It's just something I've been thinking about for the past few months, because I've been toying around with string diagrams in particular, and with other kinds of structures, and seeing what is a nice way to play with things. And I've seen that I've discovered that a lot of these structures have a particular symmetry inherent in them that makes it potentially easier to work with. But all of this is, well, based and inspired by a lot of previous work on string diagrams and hypergraphs, and even more than a century ago, the philosopher and chemist Peirce. And I kind of, the fact that that connection was there is kind of like I call it cosmic coincidence, but I think it's always kind of been in the back of my mind. But I'll give you some definitions, and if there's any questions or for any suggestions of like maybe some other people have thought about this or like references, it would be glad to discuss or like share it with us. And I think what we'll do, you can post questions in the chat, I think. If you want to speak out loud, you can raise your hand and ask something about it. And of course, in order to be accessible, I'll try to be as so this is the I'll balance the line between formal and informal because I want to be a bit vague, so it's not like it's accessible, but it can also be confusing. So if the line kind of wavers the wrong direction, let me know. So let me just see the kind of structure that I kind of arose at, which are these relational molecules. And the name of relational molecules, I don't know if it's actually the syntax or the model. So what the name refers to, but the idea is it is a description of relation. The general idea of the structure is to build relations by using atoms and building them up into molecules. And what do I mean by atoms? And so I'm being kind of specifically, well, let's say non-general or like restrictive in what they can be, so they're nicer to play with, right? So what I kind of imagine an atom to be is just a well, like in real life, it's kind of some named element and has a bunch of connections. And then the idea is that for these atoms, when you use them, they have the symmetry where any connection can be swapped. So whatever meaning they have, the order in which they are connected should not matter. And I'll give some examples in a bit, but the realization is that a lot of that can be done using these structures with the symmetry. And the idea is that maybe from a more mathematical perspective, that I'm building a potential model for this would be relations where these are effectively n-ary proposition or like propositions on n-ary tuples that are invariant under swapping, basically. So when you have atoms, you can build molecules. And so composition of molecules is quite difficult to formally define. But when we draw it, it's a bit simpler where we just take a bunch of atoms and then we connect up as many, well, whichever ends you want, and then you have some ends that are left over. And then you can see this as one molecule. Now, the big difference between an atom and the molecule is that because they are now composed, even though the atoms have this symmetry, the molecule may not have this symmetry. So like you have maybe this combination of this atom with this atom. This is not doesn't have the same meaning as this one because here this relation is somewhere else. So even though the atoms have this symmetry, the molecule does not have this symmetry. And so the question is what kind of relational structures and what kind of theories can be used, well, can be built up with just these kind of symmetric components. Maybe a notation that the molecules, we may draw an anchor point just to make sure that you know how they are oriented and that it matters. But it doesn't matter too much for the rest of this talk. How is everyone doing at this point? Maybe. Are there any?
I have a question.
Hmm?
When you
Sure.
said molecules may not have symmetry, I see that the second one is just rotating the first picture. So is that not something we call symmetry? Or
Sorry, what's second? Oh, yeah, this
the
question.
second in the molecule picture, the
Mhm.
second picture, isn't that
Yeah.
just a rotation of the first picture?
Yeah. So
Or,
yeah. So indeed, that this is indeed a rotation, but the meaning is different, and we'll see an example of this
okay.
in a bit. But if you are here, you're careful on what you connect, right? Maybe this is just like something that like cuts the connection, for instance. Then connecting here one element, two element, three elements, the same way as here with this one element, two element, three elements, the same three elements at the same positions. The meaning of the thing will be different because here this other atom is in between connected to this element, and here this one is connected to this element. So
I see. So there is
Though you,
stuff outside that they are connected to that we are
yes,
not
so
seeing. Okay.
so yes, in the context where this is connected to other things, this becomes different. Yeah. If these are just loose ends, it will indeed the symmetry will be maintained. That is true. I
So are the molecules like black boxes? Like that's why like it's not symmetry. The symmetry doesn't hold under rotation.
yes. So if you don't know what's in there, like you can think of this as a more general relation that doesn't have this symmetry, and atoms as something that have the symmetry. And you can think of it as a black box in the same way. So you compose this into this, and then you can give it a name, right? And so it's some other relation that has a different name. And we'll see in a bit that addition is an example of that can be done. Additions over a group. But yes.
Can I ask, might it be useful to have labeling then for the ports for these externally visible strings so that you can instantiate the symmetry breaking?
Yes, yeah. So that's maybe a bit useful here. I think I forgot to draw the anchor point. Another way to think of it is actually have the anchor point here. And then if the anchor point is here, then it's different, of course. If the anchor point is here, then it's maybe I should have done that. So once you use the anchor point and the orientation and the order, I mean it's a way to draw more complicated to to show that it is that the orientation matters.
I wonder if this is a point where just changing the example for no swapping might be worth doing, because it feels like you're getting into too much detail about the symmetry for the point. So maybe, yeah, I was actually thinking about this as when it came up, the just having a slightly different example might avoid these questions of symmetry that you don't really want to get into right now. They might be interesting later.
Yes, yeah. Yes. So I don't know if the example about the symmetry is another slide, but there is an example in the next slide. So I'll just start in that, and we'll see a bit later in the talk. We'll see an example where the symmetry is broken, even though the atoms have that symmetry. So which structures can be described with molecules? Now, the canonical example, or like the big example that everyone always talks about in string diagrams and other situations that has its origins in Peirce's work, in his work on existential graph, is the tri-identity relation, which as a relation connects things and then asserts that they must all be equal. So if you think of it as a relation, it relates things of the same domain, and they must all be equal. And of course, equality, like it does, if you swap the elements, then this equality is well, it has the same meaning, right? And we can axiomatize other rules. So here you may ask yourself, this is a molecule where you're combining these two atoms in this way, where you're connecting up the middle, and this is another way to connect them, right? And so here I think, yeah, it may be better to label them, but I was actually wanted to avoid using letters. But here we care about the position of the outgoing wire. In these composite diagrams, we care about the positions of the outgoing wires. But here, if we do the equality, we still have these connections. So if you say that these three are equal, and then say that these three are equal, then it's the same as saying that these three are equal and then these three are equal. And this implements what you can call Frobenius equations. It's also, if you twist your head, you can also see that it's the same as associativity in this context, where there's we kind of got rid of any kind of orientation, and we're just in this plane. Similarly, we can have this thing where if we have say this is equal to this, and then say this and this is equal to this, then it's the same as just saying that it's just a connection, what you would say a line of identity. And so this is just saying that this is equal to this. And now in this unoriented world, these two axioms are actually enough to do any other kind of construction. You can prove other things, for instance. So if you have this diagram here, this triangle, you can show that this is the same as this diagram here by using this, rewriting into this, and then using this to get rid of this, basically. And similarly, we can have like a unit by connecting up two ends to itself. Then we can use this rule again to connect it, reorient it like this, and then use this rule to get rid of this. So you can kind of get a unitality rule where if you have any kind of this kind of object being connected to this, then it's like you don't have any connection here. And this is enough to kind of define other general atoms using just this atom, where you can now define any number of connections, n-ary connections, which still have which can still be seen as atoms, but can be constructed in this way. And so you have other rules like this, where you can add more, you can combine these kind of starfish spider-like structures into one spider. And if you have a loop, you can get rid of that loop, basically. All right, so I think if are any questions at this point, please go ahead. I'll go and share something else at this stage, if that's okay. So let me see. So why is this nice? And I hope you can see this screen. It should have enlarged it. Well, because in this kind of, in this kind of world, we kind of have a world where we can start playing with these structures where we have the symmetry. So here we can think of these as this tri-identity, but here we only care about the equations, right? We don't care about the model. And these are these atoms, basically, where if you drag it around, doesn't matter. And here they are actually labeled by color. So I think I've already solved one of the issues that people had. And then what you can do, then these are open ends, and then you can connect them, right? So by dragging them over, and now you have, and now they start looking more like actual atoms. So, and then another one here, right? And then, so, but then we can ask yourself, like, how do they react? So one rule is that if you now combine these, it's like, it does the reduction immediately. So it was two connections, became one connection, then it got rid of it. And so we can actually encode the rules of the game, or the rules of the structure by having the underlying structure deal with it. So we can maybe turn fuse on to have that it actually starts connecting and merging things into one structure. And you see that the colors stay the same, right? And then if you maybe do this connection, it just gets rid of that one, because that's another rule. All right. So I wonder if it is actually possible to go back to the slides without going out all the way. All right. So now let's look at an example. So this is all well and good, but this is just spiders. This is just things that are connected. And in the end, we just get the theory of partitions, I suppose, if we just have this kind of identical structure. Priya, is there a question? Yes. Hello? Oh. Okay. No question.
Actually, I was going to ask Niels a quick question. when you turned the merging on and off, or rather when it was off in the beginning, it seemed possible, for example, to create, square structures or larger loop structures. Whereas, of course, that wouldn't be possible as soon as you make one connection with a merge, they will just disappear.
Yes.
So do you think something interesting going on in terms of the order in which you turn on and off the operations?
Yes. So the thing is that the way that I imagine it, and so with just the identity, there's not that much going on. But what I imagine is that you define some big structure as trying to solve some problem or something by drawing all these connections and then turning the rules on, and it like normalizing and simplifying it, and possibly kind of revealing if there's a simpler way of representing the same thing.
It is in that context that I'm wondering whether you think that the order in which you turn on the rules might make a difference in how the simplification proceeds, or in the final product.
In the final product, I know it will not always go to the same normal form regardless. I think there's a random aspect.
Oh, okay, all right.
In there, or not random, or like it's ordered. So I'm not going to say this like it is normalizing, but there are multiple different normalizing things. I mean, in what I just showed you, it's always a spider, always just spiders, right? But
okay,
it should, yeah. I mean, this has to do with the fuse, but we'll go into this a little bit. So let's see if there's more interesting things. So can we do other structures? And now it gets interesting for maybe a lot more people, because linear algebra is everywhere. So if you have addition, and so addition is an example of a relation that is really, it's a relation, it's really a function which does not have the symmetry of atoms, right? So if you have this, and I orient it with this anchor point here, and then this relation can be seen as A is C plus B, right? And so you have kind of think of it as two inputs and one output, or as a relation that just checks that A is B plus C. But this is not an atom, because if we swap two ends, the meaning becomes different, right? B is C plus A is not the same as A is B plus C, right? So how do we do this? Well, maybe there is some other structure, like there are other atoms that we can choose, and then we can construct the molecule of addition. And indeed, we can do this. So if we change, yes. So at this moment, I'm not assuming any commutativity. The question is, how does commutativity? I've not assumed any actions, but indeed, you would have at least swapping C and B would be a rule that you could add in this case. But of course, the goal hopefully is to get to a more to see if there are actually atoms that are at the bottom of this addition. And so one choice that we can do is think of the zero node atoms. And what the zero node atoms, we can think of them, they're kind of a family of atoms like we had before with the equality. And what it means is that in this case, all the connected things added together is zero. So if it's just two things, then it's just A plus B is zero, meaning that it is actually negation, right? So the bottom is minus the top. And another one is when you have three of them, and you can say A, B, and C. A plus B plus C is zero. And so we get, this is a very elementary linear equation. And now with these two, we can actually redefine addition as a molecule using these two ends. And so we can construct addition by doing this tri-zero sum and then the negation. So we can think of what this happens. So if this is A and B, right? in the middle, we should have an element that plus A plus B should be 0, right? So in the middle, we have minus A minus B. And then here, there should be another element that plus minus A minus B is 0. So this is A plus B. And so now we have A plus B going out. Ah, okay. We have Powell is noting that flexsymmetric or flexsymmetry is the name for so there is some work on this. That is nice to know. By Tito1, I think. Powell, do you want to say something out loud?
Tito1 correct.
Mhm.
So yeah, so he did graphical linear algebra exactly in this kind of topologically more free way than it was originally done, precisely by emphasizing this thing that he calls flex symmetry. Because he started off noticing that ZX calculus is like this, this calculus that they use in quantum. So yeah, so he did precisely this example as one of his two main examples in the thesis.
Nice.
But it's really nice.
Yeah.
The thesis is really cool. You should
Nice,
check it out,
nice.
definitely.
I need to have a look at it. Yeah, I kind of arrived, maybe also kind of like, I've just been thinking about this for the past few months. I arrived here because this is like, yeah, this simplifies, or at least it reduces the number of equations that you need to implement by, but I think, the big difference, of course, with string diagrams is that here you need to do a lot more work to define and show how they compose. But in this kind of game scenario where you let the player compose, that's not as much of an issue. But it's nice. I'll need to have a look at it. All right. But I'll present the things that I've kind of seen and then go from there. So I don't actually know what the next bit is. So this is one thing to note. And similarly to the tri-identity or the black nodes, you could generalize these white nodes as well by just doing even more sums being 0, basically. Now in the game, I don't go this far. And so for the game, or at least the widget that I've drawn, I kind of think of a simpler structure, in which case we just do the same idea, but over the 2-element group. So here we're just thinking of either circuits, or you can think of them maybe as quantum states or Boolean states. And so what this now means is A plus B plus C is a big XOR, is XOR false, basically. Or of the 2-element group, sum together is 0. And then in this structure, you have some extra rules and then that we can look at here. But with just the tri-identity and this tri-XOR 0, of course, in this case, it's an interesting situation where negation doesn't do anything in this 2-element group. So we kind of get rid of negation completely. And I think maybe addition may actually be symmetric here. But yes, or addition being XOR. So this is kind of a simplified thing. And we just, with these kind of 6 rules, where we have the same 2 rules for both these two. And then we have these extra rules where this is like the bialgebra rule that people call the bialgebra rule, which just says that if we equate these and then add it with these 2 is 0, then it's the same as doing these checks twice. So this is like doing the same equation twice, right? It's the same as doing it once. And the other one is that if you connect 2 of the same things into this XOR, well, false XOR false is false, and true XOR true is false. So it's like you didn't connect anything here, and so you get the 2 units like you deleted here. All right. So now, what I did in the widget is just implement this theory So where you take these atoms, you connect them, and then you can watch them react. And then there's a bunch of rules that it implements. So I'll not go too much further into this. I'll just go quickly back to show a little bit, and then we can go into more of a discussion. So, oh, I still have it active. Right. So now we have the two rules. So we can, I have fuse is still on.
So, sorry, Niels, can I ask a quick question?
Yes.
So the white spiders fuse?
Yes, this is in XOR. Yes, they fuse.
But does that really work? I mean, because this is the white spider, the interpretation is everything adds to 0, right?
Yes, in the 2-element group in this game. So it's
Oh,
if
okay.
you
This
do,
is just okay.
if,
This is
if
over
you
the
do it,
okay. I see.
but
Because the
there's
antipode is the identity.
yeah, you can do it
Okay.
over Z,
So
but
yeah,
then you have
because
to
they
have a
can fuse. So
negation
this
in
is one of the
between.
things that Tituan also did because they can fuse, but you need to add an extra like white dot or something, right? It's like a little bit of a more interesting, more strange for being a structure. Yeah. Okay.
Yeah, I have a slide like an appendix slide of that as well. Yes, but that's indeed nice. So you can fuse them if there's a negation. But in this XOR situation, because I don't want like too many wires connecting to the same structures.
Yeah. So you're basically doing linear algebra over Z2.
Yes, exactly. So you can do this, and now if you connect two wires, it's like they're not connected. And then the other thing that you can do, what the normalization does, which I think of as a separate option, which is anytime it finds a square, it can reduce that. So, which I'll do with React, which does it like this, and then it reduces like this, and it can do it. So in case that there are more connections, it will actually not simplify the structure, but sorry, I just want one more example, and then I think we can go to discussion. So see, so in that case, it reduced it, but actually it seems to be that there are more atoms now than before it reduced, but you can still consider it as being reduced because the number of actual atoms that were used in the construction is less. But anyway, I can share the link with people so people can play around with this on HTML as well. All right. I'll go back to the slides one more time and just say that indeed there are a lot of related works. And of course, now we've learned PhD thesis by Tituan, which I will gladly read. And I'm of course inspired by a lot of existing work like Pierce's work, extensile graphs, the hypergraph categories for possible formalization, and string diagrams as well. Of course, a lot of work by Pavel and other papers related to string diagrams. And I think it is the nice thing for you to take home is just kind of think about, well, I guess there will be a lot of answers in the PhD thesis, but what other structures can be described with relational molecules? For instance, one interesting question I had was interesting to solve is, can you do like an AND gate? And it is indeed possible to do an AND gate, even though at first it seems impossible, but you can use the fact that there are relations to actually build an AND gate. And I've got it down to one extra definition of an atom and then 5 atoms combined. You can see it in the appendix. Also, another question you can think about this generalization. What are equations that you can do for this kind of linear equation systems, and what are different formalizations that you can do? I think because Pavel quickly said something about that, I can say that this is what linear algebra over Z, I think, looks like, the equations, where you also have an extra negation, and then you have this kind of Frobenius with a negation in between, basically. But I'll just say this quickly to address Paul's comment. All right. So, like I said, this is really, it's both, like, it's a combination of different areas of interest of mine, and thinking of simpler representations of things and how to play around with them. I've been experimenting in different ways as well to define or to play around with categorical structures. And of course, linear equations are used in lots of areas, or even over rings, and even like areas of security and other things. So yeah, linear algebra always is one of those courses where it takes a bit to get into, but maybe different ways to intuit are always, well, interesting.
Niels, I'm curious. So it seems like right now you have a simulation of this particular syntax, but I'm wondering, like, you know, we were talking about video games and just like game structures. I'm wondering how, like, what do you see as the pathway from this to like some kind of structured game, or like what is the interaction you have in mind for how people would actually play with this?
Oh, I see. Yeah, I guess the question is also, what's the difference between a widget and a game, I guess. Like, this is more like
well, yeah, and I mean, even just looking at it, I'm like, you can imagine a two-player game where each person has a limited set of manipulations they can make, and they're trying to race to some goal. But there's also these like solitary, like just a puzzle game where there's, you know, and I wonder how much the syntax gives way to interesting kind of puzzle design.
Yeah, so the kind of solitaire style game that I'm kind of leaning towards, or like I've been experimenting with, particularly with string diagrams, in various ways, is the idea that the target is to reduce the diagram. So a lot of these rules simplify the diagram. So you reorient things in order to get rid of things. And I had a small game where you were harvesting crystals, basically, that the nodes were crystals, and then you had to reorient it to get the crystals out. And there's another longer project that I've been part with, which is also the idea of simplifying, getting rid of crossings, and learning new rules to clean up more disorganized structures in a well, yeah, solitaire style, potentially story-based game. Another maybe quickly to say, another fun thing to try is, maybe if you just want to dual versus on this little game, is to have a bunch of atoms, take turns in connecting things, and then well, make sure that you have an odd number of atoms to start with, and then see whether the resulting unit node is white or black, and then play for different sides. Because when everything is connected, we'll always reduce to a single unit. So you can maybe do like a little dual, like versus game, where you have to keep connecting and it will reduce it until there's only one thing left, and then whoever wins. That's something to do with this with this widget as well. All right, Brendan, do you have a question?
Yeah, hello everyone. My name's Brandon Baylor. I'm an engineer in industry, but also have been on a journey of applied category theory for many years, and working closely with several in this group, and excited to participate in this conversation. Also started a nonprofit recently trying to apply category theory to develop collective technology. And so what I wanted to say, building on Paul's question and comment, is that this isn't just, I see this as not just a foundation of like a game, but how we make real business decisions in the industrial context of, you know, today we sort of lack the formality of understanding and the rules that how we put our work together, whether it's a perspective or a decision or a model. And what I love about what you shared, Niels, is that we're sort of, if we could embed the rules of the structure so that people were aware of how they put their work together, sort of generally speaking, I think that that's a powerful construct for decision making and in real business context or real context of how we make decisions. So I just wanted to say that I'm excited by this conversation because I think it would be awesome to play a video game of this nature, but I also think that we are missing a language that lets us carry meaning and brings clarity to like contradictions or overlaps when we try to put our, I see these molecules coming together and I'm thinking these are perspectives or models or decisions being made. And like today we tried to describe the underlying rules through like English language or labels or data. And if we can do it at the level of structure and have that structure visible and formalized, it just to me is very promising. So thanks for sharing. I just wanted to make that comment.
Yeah, no, thank you for your comment. I think there is a big discussion here, like where there's a lot of diagrams being used in lots of different areas, and which almost can be given a formal definition, but isn't given, is mostly used illustratively, but potentially could be given a more formal definition to say like or how different, yeah, like you said, works or like different algorithms or like components actually interact and compose and have that well, formalize that a bit more, I guess. Ted, yeah.
Yeah, I wanted to build on what Brandon said because I also had somewhat similar thoughts. First of all, I was thinking that the framework inspired me to imagine it being a way to represent satisfiability questions. And then that then made me think, okay, well, who are interested in satisfiability questions? Of course, a whole lot of people. But more recently, I had the experience in a class I teach regularly on business analytics, where we were evaluating the joint feasibility of collections of inequalities in business settings, and where formal programs would, for example, tell us whether the programs exist that can tell us the answer, but the question was, what sense do we make of that? If some sort of set of inequalities is actually impossible to satisfy, but it takes a while, and students struggled to figure out which where is the nub, where is the problem. Whereas here, this reduction algebra essentially might help visualize better where the thing breaks, where it can't, or where the disconnect in some ways is. I mean, it would appear basically as a disconnect, it seems to me. And so the way I'm seeing Brandon's comment is not so much as a sort of a solution technique, but as a communication technique, as a technique of making sense of some complex AI powered, for example, answer that we want to make sense of in a business setting, and say, okay, so let's say a business or some other setting, but some applied setting where we want to understand what blocks a certain set of constraints or requirements to be jointly satisfiable.
I think we can just go like continue our discussion. I don't know. I'm chairing a little bit, but Edmund, you wanted to say something? Oh, you're muted still.
I
Yeah.
had a previous comment on the game stuff, but also but thinking about this current discussion, there's an interesting aspect that I think comes from both of these things, that you want to use the mathematics more as metaphor. You want to sort of use it to sort of take the business idea, shake it up, and see what emerges. And one of the issues when in those settings you start to create these more mathematical processes is they start to often get regarded as mathematical models, and the model starts to become real as opposed to the thing that the model is modeling. So I think this sort of that makes a very good connection to this way of approaching these problems. The notion of compassionate mathematics is also thinking about mathematics as a more metaphorical tool at times, where you can see what you can learn, but you're not allowed to take the conclusions too exactly. So I like Ted's sort of follow up on that, which was sort of, this is more a tool for understanding than a tool for visualization, or it's for understanding rather than perception. You have to make sure you're processing what you're seeing. I mean, I think, the classic example is the way that various assessment techniques that were developed to sort of give a broad brush understanding of what teachers in mathematics were good at or bad at, then got turned into individual assessment to try and so I think one of the ideas that would need to be built into this sort of thing is that your modeling might be wrong. You need to, because you're dealing with these sort of more subtle metaphorical things when you're dealing with these in terms of business decisions. And so you put it into this model, you shake around and see what falls out, and then you need to validate that back against reality and see whether it works or not. If you can do that well, I think one of the benefits you'll get is identifying where your assumptions are wrong. Like finding out places where, like the data that you put in, the sort of group dynamics or whatever particular thing, you're putting something in, you get this conclusion, and the conclusion is clearly bullshit. Even though the input seemed sensible. And so now the question is not how do we deal with the bullshit that we got out, it's that how do we identify what was wrong in what we put in. And so, but the issue there is sort of the cultural perception of mathematics being this very precise scientific thing that is actually able to predict eclipses and things like that. And it's really good at that, but this is a slightly different environment. The other comment that I had was that I was looking at things and thinking of sort of Conway's work on sort of combinatorial games and surreal numbers and things like the game of Sprouts, and had wondered whether you'd explored whether you can put those sorts of systems into this system.
Yeah, I'll have a look at it. About the game of Sprouts, you said? Sprouts,
Yeah.
right?
Sprouts, yeah. And more broadly, there's the book on numbers in games, and Donald Knuth's book on surreal numbers.
Right.
This is kind of a oh, sorry, go ahead, Ted. I have a question. How do you raise your hand?
It's under reactions now. It took me a while.
Okay, thank you.
Sorry. So I was just gonna say, thank you, Edmund. It did also remind me of a setting that a student of mine worked on many years ago. This is maybe 12, 13 years ago. When I first started, in the first couple of years I started teaching in high school, I had a student do an independent research with me on essentially combinatorial geometry. And he, on his own, ended up developing a language that looks very similar to this. In other words, and in fact, he was thinking of it as, because he was learning chemistry at that time as well, as basically valences of, like atoms with valences. And it was the idea of counting the number of distinct configurations of points and lines in a discrete geometry model. So if you have, can you have a configuration with 6 points and 6 lines, let's say, or something like that, right? On the plane, or and so he had come up with this framework for recognizing similar configurations that are equivalent, configurations that don't look similar, or to determine which combinations are feasible, which are not. Basically, it's a way of encoding a kind of a Diophantine system of equations, for that capture the combinatorics. I had forgotten completely about that, and I was just looking for that paper. I'll have to find it, but it was very interesting that someone with no prior experience in formalization, he was probably a 10th or 11th grader at the time, came up with this with an idea like that. And so to echo, the reason I remembered this as well is because of what Edmund was saying, that very often you can be wrong in the details, because obviously he didn't solve the big problem. In fact, turns out some of these questions that he was after are sort of notoriously difficult or even impossible to formalize in that way. However, along the way, you might develop a tool that ends up being very versatile and useful for representing what it is, what the nut is, what the hardness of the problem boils down to. And so I in my limited experience with diagrammatic methods, I think they are supremely well suited for visually capturing where the rub is, where it doesn't simplify anymore or whatever. Anyway, I thought I'd say that. Thank you.
Right. I think also, so Paul raised his hand, but also if Priya said something in the comment section, what is before that?
Oh, I just said I really like the idea of what Edmund was saying, like reflecting on the process at which gave the conclusion rather than taking the conclusion as the word of truth. Like, I think that's very valuable and it's often overlooked when we do mathematics. Yeah. Also, I would like to say that so the game, not this game, like Niels was talking about a game where he was designing something with string diagrams and reducing string diagrams. I have tried this with my friends in sciences, not mathematicians, but biological sciences. The way they approach the game or solving the game is so different. They brute force it. It's like they get so frustrated. Like rather than thinking systematically, even when I play Lego with them, they will be like, if something doesn't fit, it's like, okay, I'm going to turn this and try. I'm going to turn this and try. It's like, why are you brute forcing? There is a systematic way to approach it. But it's like developing that thinking process, or importing the idea of thinking systematically into other disciplines. I think that's quite powerful, and it can be most effectively conveyed through these games. Yeah. Paul, sorry, I overtook you.
No, I was just thinking about the opportunities that you have because you're in an interactive animated environment. Is how do you justify the axioms now? Allows you to use. I was thinking there's some physical metaphors that could be handy, the tripartite thing with addition, where everything has to add up to 0 as being your building block, could actually literally be a platform with 3 people standing on it, and they have to position themselves so that the platform is balanced, and that becomes the starting point where if you move any 2 of these people, the other one will move such that the thing is balanced. And now it starts as a sort of physical metaphor for that dynamic. And actually, the other thing is multiplication. You can have a multiplicative relation where everything has to multiply up to 1. And I think the metaphor there would have to be people have a volume that has, the volume is always 1 and 3 people control the sides of a parallelepiped. And then if you connect those people up, now you're starting to build a system of physical things that are all self-equilibrating. And then you can I don't know, the opportunity to do some storytelling at the level of how you motivate those axioms in the first place seems like a real opportunity for building things in a game engine. Anyway, I was trying to visualize what that could look like. I wanted to share that thought.
Yeah, nice. I think on the general discussion on using storytelling for mathematics,
Yeah.
is a whole other topic, I believe. But this, and I like to combine all these aspects into one thing, but I'm also just experimenting on the right rules or what's the nicest representation. And so this is part of that. Indeed. But yeah, there are some nice ideas. Yeah, kind of like a game semantics, almost like game semantics, but it's both a game and game semantics, basically. Yeah. So let's see. So I think we should stop probably at 8, just for scheduling, people scheduling. But I see that 2 people have now raised their hand again. So Edmund, you raised your hand first, right?
This was a quick thing in response to Paul's comment. It's can you create a system like this where you put in fractions and they reduce to fractions in lowest form, and so you're therefore handling numbers and rational numbers.
Yes, taking the tedious work out of the hands of the the person playing around with it, basically. Yeah.
But not so much taking but seeing the relationship and seeing what minimal form is, and why you might want to be able to reduce. So you've got this idea of taking some object and reducing it into a canonical form. And
Yes.
the one that students struggle with is rational numbers. That's a really hard concept.
Yes.
And showing that, one of the ways I introduce it, point out to math majors, is that we don't solve a problem by introducing a rational number. We just write down the problem, but we need to show the equivalence. It's not equivalence between numbers, it's equivalence between problems. And so 2/3 is the same problem as 4/6, but we leave it as the 2 divided by 3. We still write it as a question, but we want to be able to identify when 2 things are the same, and it's easier to see, are these things identical, as opposed, so being able to see that notion of reducing so you can tell when things are the same, sort of is inherent in this. And it would be a nice way to get students to understand why you want to find GCD and divide by it top and bottom. So
Yes.
Niels, I have a quick question, like different from what we have been discussing. What's your next step in this game? Like, where do you want to see it go?
I wanted to quickly implement just like a solitaire reducing version of this directionless version. I'm kind of just imagine exploring a temple and then getting like collecting these nodes basically by reducing them and then kind of learning more rules just to see how that works. Of course, there's the other project that we've been involved with, which we can also kind of pick up and push again. But so the general framework that really got this started was just the idea of just being in the world and interacting with mathematical objects. So you just take this and take that and then just collide them and see what happens, basically. And then have it as well a world where you're like, yeah, you're exploring and you're finding it, and then you're combine it and just turning it into exploration and discovery instead. So a framework like that. That's one way that I was also thinking about it. So I'm still experimenting on all these things.
Very nice. Edmund has a comment. He said, not related to the discussion, but I would love to know more about the springy rules for the movement of the atoms. That was impressive.
Oh, the springy rules.
Like the atoms were bouncing. It's kind of when you moved, it's not a linear movement. It's like,
Yeah. So there are 2 rules. One is that it's trying to be at the same distance from each other, and then it will just like push away and pull. And the other thing is it will keep track of all the directions. It will figure out the average direction. Well, it does some average over direction, and it will figure out how much the discrepancy is, and it will push any connection into the direction that it should be, basically. So it's both differences being corrected and it's trying to evenly spread out all its neighbors. And then you just like change the variable or the constants until it looks nice, I guess.
But it was a really nice aspect of those things. It turned something that could have easily been very geometric into something that had a character and personality to it that sort of fitted, and it was sort of an important part of the illustration. I felt, without it being part of the underlying structure. So that was nice.
Yeah, another problem is that it, of course, will get rid of nodes that have two connections, but sometimes you want to keep them just so you have a little bit more. So I mean, the question of, because if you connect a lot, you just get a garbled mess. So I don't know what to do with that. Basically, like trying to clean this up, which is why I was also thinking about planar graphs, basically, where you have explicit crossings, which already kind of clean up a lot of this mess. So you can do the theory where the atoms are not completely have permutation, but just rotational symmetry, and then have explicit crossings, and then have the structures like that. And they tend to be cleaner. And so
that relates back to Ted's comment about thinking about discrete geometry and thinking about, you've got your zero and one-dimensional structures, but how do they combine into two-dimensional structures?
So we are almost, actually, we are running over time, but we have, like, I would like to read like the comment from Ted, and then we would thank Niels. So Ted says, I think the reduction to different standard forms is a central aspect of any sense-making process, and he wonders if this framework can help visualize in a metaphorical way this reduction. Any quick comment about it, Niels?
yeah, probably, yes.
Okay, we can
Yeah,
take.
I don't know, in the metaphorical way. So are we talking stories now, or yeah?
What I have in mind is, think of polynomials, right? And whether, there are different standard forms for polynomials, let's say.
Yeah.
Right? And can you use a framework of this kind to represent, factored form versus, whatever. So,
Well, yeah.
or even in logical, in CNF or whatever, different like forms of a statement, of a sentence.
Yes.
Because
Well, what the game is kind of doing is reducing matrices, right? Because we have a bunch of equations,
yeah.
and it reduces and then it adds them. But then some reductions of matrices are different. So that's why I was saying before that it was.
But reduction in linear algebra over Z2 is essentially solving systems of, first order equations, essentially, logical equations. So I'm just saying, I'm thinking of, it's not obvious to me yet, but standard forms are basically combinations of, they're basically logical statements almost, right? So if you have to translate the standard form you're interested in into a logical statement of, it has these many inputs, this many, it's in this sequence. It's almost like reparenthesizing or changing the order in which you're doing an operation, right? So
Yes.
And it would mean figuring out what the right axioms are. So it's a little bit like what Paul was talking about earlier, like, in gamifying what the axioms are, like playing with what the axioms are so that you can see whether you can get that representation of a particular standard form you're interested in. And then the game itself is getting there, is getting to that form. Like, anyway.
Yes.
Something to think about. I'm not sure if the answer is right, but.
Okay. Thanks, Ted. Okay, thanks everyone for the great discussion. I think this is a great start to this series, and I really enjoyed it. Hope you all too enjoyed this discussion. Let's thank Niels. And Niels, your game was super cool, super creative. Okay.
Thank you. How shall I share the link to the game?
Maybe I could email everyone the link after the talk once I receive it from Niels. Okay. We hope to have our next talk next month, but yeah, watch out for the details. Like I'll be in touch with all of you. Thanks everyone. Bye.
Thank you all.